start the fourth unit, that is oscillation and power amplifier. Okay. But before going to start that unit, let me cover some miscellaneous topic which I couldn't complete yet. We'll complete it first, then we'll switch to the fourth unit. Okay. So first topic of the day is current mirror circuit. Current mirror circuit. Or also the another name is constant current provider circuit. Constant current source, I can say. Okay. So what is the current mirror? Let me draw the circuit first. The circuit for the current mirror is, you can see over here, perfectly fine. They are common to each other. This is the terminal, collected terminal of the Q2. Two transistors will be connected in this way, and this will be common for both of them. Here the collector and base will be connected over here. Now what current mirror concept says? The current mirror says, as the name suggests, the current will be mirror Q1 and Q2. Current mirror says if the current over here is I reference or IC, same current will flow over here also. This is the current mirror concept. Is it okay, friends? So two BJTs are connected in this way, Q1 and Q2, and the base is common for both of them, or base is connected at single point. So the collector current is equal to the, or I can say the IC1 is equal to IC2 in this case. How is it possible? Let's just see it. Okay. So current in this, suppose let's take IC. Okay, so base current will be what? Tell me. The base current for this transistor will be definitely IC by beta, because you know the relation between IC and beta. IC is nothing but beta times of IB. So IB will be definitely IC by beta if you know the value of IC. Okay, correct, no problem at all. And both are identical. So this one Q2 also fetch the current, that is IC by beta. Is that okay, friends? What it means, in this branch you are getting 2 IC by beta current. Is it okay? Okay, friends. So this current, the base current is IC by beta for Q2. What will be the collector current for this? Definitely it will be IC. It will be IC or not? Tell me. You know the when you multiply this quantity with beta, you will get IC. Okay. Now friends, what current mirror circuit is saying, this I reference is the current from this source is equal to this IC. The concept says I reference equal to IC. Is it okay? But I reference, how it become IC? See, here in this case, in this branch the current is going 2 IC by beta. In this branch the current is going only IC, and I reference is summation of both of them. If you will apply the nodal analysis at this point, you will get I reference equal to this plus this. So both current IC plus 2 IC by beta will add like this. Is it okay? Now why we are saying that I reference is equal to IC? Why? See friends, this beta is very large. This beta is very large. So beta is large. So this quantity is very low. If this quantity is very low, so I can say I reference is nearly equal to IC. Okay. So here is the assumption that IC is equal to I reference. That's why we are saying it's current mirror circuit. Is it okay, friends? So let me take one question or illustration of this, so it will be clear to you. Okay. So the question is given They are connected like this. Here it's RC. RC is connected Q2. In Q2, current is 5 milliampere. Perfectly fine. Over here, you applied V in. Ground it. Over here, you have R. Fine. Like this. And this is minus VEE. And that's given minus 2.7. Okay. So, friends, here the voltage is given 3 volt. It's 3 volt over here. No problem at all. Now, what will be the value of R? See, they're asking what will be the value of R for the current mirror. For the constant, to develop the constant current source, what will be the value of R? This R value they're asking. So, constant mirror. So, do you know the current in this? Yes, we know. See, this is the 5 milliampere. The same current will flow over here also, 5 milliampere. So, same current will flow to this circuit also, 5 milliampere, because two transistors are connected. Wait a minute. I forgot to draw another one. Over here, we have another transistor, like this. Okay. Wait, let me correct it. Here are the two transistors, Q1 and Q2. That one is another one. And the question says, they are connected like this, and this. This is minus 2.7. Here, the collector is connected with this base. These two terminals are connected. Now, if you will observe this circuit, this is the current mirror circuit. Where it's Q1 and here it's Q2. Now, the question is, to make it constant current device, what should be the value of R? Is it okay? And the 5 milliampere is given over here in between. Here 5 milliampere is given. Okay, friends. So, if this is 5 milliampere, let me do it properly. You will not confuse. The 5 milliampere current is given in between two transistors, means IE of the upper one. Let me draw it properly so it will be clear to you. Here the transistor is given like this. They are connected to each other. Here they are applied V in and grounded. The current over here is given 5 milliampere. So by the current mirror, this 5 ampere same current will flow to this also. Remember, we discussed this is the I reference. This is I reference and this is IC. So you have IC 5 milliampere. Definitely I reference will be 5 milliampere. Okay, perfectly fine. Now they're asking about this R. How can we find this R? To find R, you need potential difference and current. You have current, okay, no problem, but you don't have potential difference. Are you getting? For the R, see, this is the current and we know V equal to Ri. I is nothing but V by R. This is V is the potential difference. So this, at this point A, the potential is 3. What about this point? VB. So minus VB divided by R we have to find out, and the value of current is given 5 milli. Now the question is, what is VB? See friends, this is 2.7 given. Is it okay? Can I start my journey with VB? I'll start my journey from VB. I'll move to the circuit and I'll come to the ground. Okay, so what value I'm getting? Okay, so let's start with VB. VB. Here we came like this, and here this is plus minus 0.7. So minus 0.7. Here I came and this is 2.7 equal to 0. So VB is equal to minus 2 volt. Is it okay, friends? So VB is equal to minus 2 volt. Am I right? Yes. Now you can apply it into this formula. You will get 3 minus 2 divided by R equal to 5 milli. So this is nothing but 5 divided by R equal to 5 milli. So R is definitely 1 kilo ohm in this circuit. Is it okay? So this is current mirror concept. Okay. Now let's see this circuit. In this circuit, the BJTs are connected in this way. I'm sorry for this. Let me do it again. Here is Q1. This is Q1, okay? And the remaining are connected in this way. At the output stage, I have parallel combination of Q2, Q3, Q4. Like this. Base are connected. All base are connected. Okay, this is the collector terminal over here, over here, over here. And this is common branch for all. This is the circuit, suppose. Okay, in this case, if this is I, so definitely by current mirror, this will be I, this will be I, and this will also I. So if these three are I's, so this will be definitely 3I. So this is the parallel kind of thing. This BJTs Q2, Q3 and Q4 are connected in parallel circuit. So what will be the total output resistance? If we have at the output stage, suppose we have resistance R0, it will be definitely decreased. Why? Because in the parallel combination, resistances are going to decrease. Is it okay? So remember this thing. If this type of circuit will come, don't assume this current is I. Okay, this current is not I. If this is given, so the collector currents are I for all, not this entire current are I. Okay, so sometimes students make mistake over here only. That's why I showed you. Okay. Now we'll see the current mirror with emitter resistance. We'll see current mirror with emitter resistors. Okay friends, in this case with BJTs we'll be having emitter resistance also. Let me draw the circuit. This is the circuit given over here. Let's take it RE1. Two transistors are connected. Okay. This is RE2. Grounded. Emitter, emitter. This is given I reference, suppose. And this is I node. So what will be the, and this two things are connected. So what is the output for current mirror circuit? Or current mirror emitter resistor, right? So friends, please tell me one thing. The voltage, if this is voltage VA. So voltage is same for this all two or not? Tell me. First of all, tell me one thing. Because here plus minus 0.7, plus minus 0.7. If these currents are equal, so these currents are also equal over here. So voltage drop of this branch up to here is equal to voltage drop of this branch or not? Tell me. If it is yes, then let me clear some parts. Okay. Wait a minute. So 0.7, 0.7 both are same in both cases, so it will be gone out. Here the current is I reference. Here the resistor is RE2 and current is I node. The voltages are equal, means RE1 into I reference equal to RE2 into I node. Correct? Like this. So this is the relation. If current in the current mirror circuit you have emitter resistance, it means the I reference and I node ratio is RE2 divided by RE1. Is it okay, friends? So this is the formula. Now let's come to the topic 2. of the day, okay? And that topic is slew rate. Okay friends, so we have seen what is the slew rate formula. Now we'll see something in details. So slew rate, it is the maximum rate of change of output with respect to time. Is it okay? What it means, see, we have seen the formula that dV naught by dt. This is nothing but our slew rate. Okay. So maximum rate change of output for all input signals. What it means, see, if you have some circuit, let me take circuit with negative feedback. Over here R, here you are taking V naught, and this is non-inverting terminal where you are applying some V in. Is it okay friends? So what is going on over here? Suppose at the input stage at V in you are applying step input of 5 like this. Means at t equal to 0, you have just applied the 5 volt to the circuit. Is it okay? But if you will get the output, you will not get it sudden at t equal to 0 the same thing. It will take some time. Okay? It will take some time like this. After some time it will come step. Step you applied, we have to at output stage also the step, but the step is not going coming at sudden. See, as you applied the input, immediately you will not get the step over the output stage. Okay, it will be increased like this. In this way it will move to step. Okay, so this is the time in microsecond actually. Okay, so what is this? This is the rate change of voltage or not? This is dV naught by dt or not? And what should it be? It should be infinity. Ideally it should be infinity. Why infinity? Infinity means at 0 time it should change itself. Means what we want. What will be the good for our circuit? This one will good, or this one will good, or this one will good. Whoever is close to step at 0 should be our output. Is it okay? So what is our requirement? Our requirement is the slew rate. Slew rate means rate change of output with all inputs, with respect to all input signals, should be maximum. Maximum means should be infinity. Why infinity? Instead of micro, your need will be, it should change in nanosecond. So dV naught by nanosecond, it means it will be in the order of 10 to the power 9. So we need over here 0 time. If we'll keep 0 over here, it will be infinity. So slew rate of the system should be infinity. Okay, ideally. Okay, now let me tell you one thing. That we are having two things. One is, we have two things. Slew rate of op-amp and slew rate of input signal. Input signal. So we have two slew rates, okay? Slew rate of op-amp and slew rate of input signal. See friends, this is our op-amp, and to this op-amp you are applying your input signal. Is it okay? And you are getting output signal. So you are getting some slew rate over here. Okay, and that slew rate is change in output, means rate change of output. Is it okay? So what I am saying is, why we are getting this slew rate? Your signal is now moving like this. Instead of direct step at t equal to 0, it's taking some time. Why it's taking some time? Because of this op-amp, right? At the input signal, there is no problem. At t equal to 0, you are getting direct step over here. But at the output, you are not getting step at t equal to 0. You are getting after some time delay. Who introduced this time delay? The op-amp circuit. So what I am saying is, the slew rate of op-amp means the rate change of the signal in op-amp should be greater equal to the input signal. Means the input change, before that your op-amp should change itself. Okay, or your op-amp should keep it ready itself for change in input. Means immediately, if your input is changing, the same thing should occur in the output. Is it okay? Means, overall I'm saying is, the delay time should be 0. Delay time should be 0. Means slew rate of op-amp should be very high. So I can say that slew rate of op-amp should be greater or equal to slew rate of signal. Always remember this. Okay, means op-amp should change itself faster than signal. So you'll get without distorted or the proper output. Whatever input we are applying, and you will get the output. Okay, so let me take problem over there based on this concept. So let's consider output is sinusoidal, and that is VO max sin omega t. Let's consider this is the output waveform. Okay, now what slew rate says, slew rate is dV naught by dt. Okay, so we have to differentiate it. dV naught by dt is nothing but this will be V naught max, sin will become cos omega t into omega also. So ultimately you are getting V max into omega and cos omega t. This is the slew rate of what? Signal. Is it okay? This is the slew rate of signal. And when it will be max? Slew rate max. Slew rate max will be the maximum value of cos omega t is 1. So it will be V max into omega. Is it okay? And when we will expand this, we can write it like 2 pi f max of V. Is it okay? V is V max over here. Can I write like this? This is the maximum slew rate of signal. And what is the condition? What is the condition? The condition is the slew rate of op-amp should be greater or equal to slew rate of signal. Means it should be greater than 2 pi f max into V max. Is it okay, friends? This is the condition for slew rate. Now I'll take one problem. The question is, the op-amp has a slew rate of 1 volt per microsecond with a gain of 40 dB. The gain is also given, that is 40 dB. Okay. If this amplifier has the faithfully amplified sinusoidal signal from 0 to 20 kilohertz, we are applying this input to this amplifier and we are getting faithful output. Means whatever we are applying, we want the same at the output stage. So what must be maximum input level, they are asking. What should be maximum input level? The question is, what should be maximum input level? Okay. So friends, F max is given. See the op-amp slew rate, the formula is the op-amp slew rate should be greater or equal to 2 pi F max V max. Is it okay? Now, this is max and this is V naught max, right? So, this one is given in the question, that is, let me change the color. This one is given and given value is 1 volt microsecond. Okay, perfectly fine. 2 pi. They have given the F max also 0 to 20k, so it's a 20k. So we can calculate V naught max, we can calculate. Correct? So keep this V naught max this side and take all this to this side and take it just equal. Okay, because we are calculating the maximum input requirement. So everything will go this side. So when you will calculate, you will get V max equal to 7.95 volt. Okay. And this will be given in the options also, 7.95. The first option is given this one only. Second option is given, C and D also given. Immediately students, 80% students will check this, 7.95 volt. See, what is the question? The question is maximum input they are asking. They are asking Vmax of input. And what we have? We have V0 max. They are asking V in max. Okay, that's why this gain is given over here. So, now let me check. What is gain? Gain is V0 divided by V in. But gain is given in dB. So let's take 20 log V0 by V in. Is it okay? And this gain is given now 40 dB. So this is 2 log V0 by V in. Okay? Because of this 2. Let's take antilog both sides. It will be 10 to the power 2 V0 by V in. Okay, friends. So V in will be V0 divided by 100. So it will be 7.95 divided by 100. So I can write it 79.5 millivolt. This should be the maximum voltage we can apply. Okay, so we'll get the output perfect whatever we want. So the third topic of the day is filters. Okay, filters. So I think you heard so many filters, that LPF, low pass filter, high pass filter, band pass filter and band reject filter. Okay, in all these filters we check the amplitude or magnitude, but in the all pass filter we deal with the phase change only. Is it okay? So let me start the filters. We'll see some circuits for all filters, so it will be clear to you. And here I have to introduce the omega 3 dB concept. So the first one is, please identify this. Which one is this? This is the LPF. Okay, this omega is C is the cutoff frequency. This is the ideal, but in actual the graph will be, let me draw for all first, then I'll show you. So this is for low pass filter and this is for the ideal, but in actual the characteristic will be like this. Like this it will go. And if you'll observe this high pass filter, it will be like this. And this is the band pass. So this is like this. This is particular band reject. So this is practically we will see, and this is all pass filter. So this one is LPF. LPF, this is HPF, passing high frequency, passing low frequencies. This is band pass and this is band reject. Okay friends. Now if we'll see the relation V0 by V in, so what will be for LPF? Let's see. So for transfer function, or in other words I can say the transfer function for LPF should be K divided by 1 plus S tau. K divided by 1 plus S tau. Definitely it should be like this only. Okay. If you draw the Bode plot of this transfer function, I think you know about this. Means the K is constant and at some value of omega, is it okay? 1 by tau over here, minus 1 by tau. We are adding the pole over here. Pole means it will go to minus 40 dB decay and will come to at 0 level. Okay. If we'll talk about the transfer function of HPF, it will be Ks 1 plus s tau. K is 1 plus s tau. Okay. At origin we are adding 1 0 and we are adding one pole at minus 1 by tau. Is it okay? So it will be definitely like this. What about band pass filter? See, in this band pass filter we are getting two frequencies. This is omega L, lower cutoff frequency, higher cutoff frequency. Okay. So in this case, in the band pass filter, this is the combination of low pass and HPF something. So I can take it, for this I can take it 1 plus s tau 1. Okay, perfectly fine. And multiply with this also. So we'll get s over here and I'll take another one. S 2 poles. Okay. Now if we will take the generalized form, it will be Ks divided by second order s square 2 del omega naught s plus omega naught square. Is it okay? This is the standard second order form for band pass filter. Okay friends, we'll talk about the band reject filter. It will be simply K s square plus omega naught square divided by s square plus 2 del omega naught s plus omega naught square. Is it okay friends? And for the all pass filter, this is s minus a, s plus a. Simply one, if pole is this side, at the same time 0 will be opposite side. Okay friends? So this is the condition. Now very important, you can directly remember this. Sometimes they are asked direct questions. Now here the concept of omega 3 dB is very famous. Omega 3 dB is very famous. So let's take the first example, LPF. The gain was 1 divided by, or let's say K divided by 1 plus s tau. Is it okay? This was the gain. What is the magnitude of this? Let's take magnitude. It will be 1 plus omega tau square under root. Okay? This is gain. Now omega 3 dB frequency is the frequency where the gain becomes K by root 2. Initially the K is max, so the gain will become K by root 2. Is it okay? I'll show you like this. If this is the graph we have drawn between K means magnitude and omega, the graph is like this. For this particular, this is the low pass filter, definitely the graph will be like this. Now someone is asking, in the examination they are asking, find out the omega 3 dB. They will give some transfer function definitely. And they will ask, find out the omega 3 dB. So what we have to do, see. Omega 3 dB is the frequency where the magnitude, this is omega 3 dB if suppose. So at this frequency, the magnitude will not K, magnitude will be K by root 2. Or in other words, the magnitude will be 0.707 of actual value. Okay, so omega 3 dB is the frequency where the input magnitude is 0.707 of the original one. Okay, so friends, let me tell you one thing over here. So for this transfer function, if he is asking what is omega 3 dB, so omega 3 dB is the frequency at which the gain become K by root 2. So this is K by root 2 equal to K 1 plus, now frequency become omega 3 dB, tau whole square under root. K will get cancelled and you have to square both sides. You will get omega 3 dB into tau square equal to root 2 and it should become 2. Is it okay? Omega 3 dB tau square equal to 1. So finally we are getting omega 3 dB is equal to 1 by tau. Whatever time constant is there, just take inverse of it and that is the omega 3 dB. Is it okay? See, here is the time constant omega tau. We are taking 1 by tau and 1 by tau is nothing but the omega 3 dB. Is it okay friends? Over here in the transfer function, the multiplier of s is nothing but tau and 1 by tau came the omega 3 dB. Okay. Now we'll see the circuit diagram for all filters. Okay. So for the LPF first we'll see. For the LPF the diagram is, this is low pass filter, R given over here, capacitor is connected over here. The circuit is like this. This is the low pass filter and we have seen the characteristics graph already. Okay. Now this is LPF. What if it's HPF? HPF. So you need to change the position of your capacitor, right? Now in this case you will get higher frequency because low frequency will be blocked over here, output will get 0. At higher frequency it will be short, so we will get over here the output. Okay. Now if I'll talk about the BPF, so BPF diagram is two stages of this two, means first take HPF. In the BPFC, this is the BPF, right? So in BPF first we introduce the HPF and then we introduce the concept of LPF. So first HPF circuit, no problem at all. This is HPF circuit. Input you applied over here, and next LPF circuit. This is LPF circuit we have seen already. So this circuit is your BPF circuit. Okay friends, now let's come to the this is the again Laplace, this is again a low pass filter. In the low pass filter we can use second order low pass filter. If we want to design, we need two memory elements. So here I can use inductor also in this way. So this is also low pass filter. This is also low pass filter. At very low frequency this will be short and this will not work. So entire input whatever you are applying over here, it will come to output. Means the low frequencies are passing by this circuit. But if we will take the high frequencies, in the high frequencies the capacitor becomes short circuited. Once it becomes short circuited, the output will be 0. Okay. Now let's come to the BSF or band reject filter. Band stop filter you can say, and band reject filter also. So in the reject filter the circuit is the inductor and capacitor, they are connected in parallel. The combination of these two is creating this band reject filter phenomena. Okay, this is R over here connected with V in. So this circuit is for band reject filter or band stop filter. Okay friends, in the band stop filter the inductor and capacitor will be connected in parallel. Okay, now I'll give you something, and you have to identify them. Okay, the circuit is given minus plus. Here I'm taking V0. This is R2 connected over here. At the input stage we have capacitor C1 and resistor R1, and to R1 V1 is connected. Now they're asking which type of filter it is and find out omega 3 dB. Omega 3 dB we have to find and filter we have to find. So for omega 3 dB definitely we need the transfer function. Okay, so we'll know the transfer function for this also. So this is 0. How to convert capacitor in S domain? It will be 1 by Cs. Now you can remove this. Everything is resistors, so resistors will be as it is. Okay. Now my question is which type of filter it is. So directly by seeing we can judge it whether it's low pass filter, high pass, band reject part. See, at the omega equal to 0 means very low frequency. What will be the status of this? This will be open circuit. This will be open circuit. No connection with input. But this ground concept will be connected over here. So output, what you are getting output? We are getting 0. Because this 0 is directly connected over V0 now. So in this case you are getting output is 0, means this filter is not passing the lower frequency. Now what about the upper frequencies? upper frequency sets infinity. You have to check for omega equal to 0 and for omega equal to infinity. Omega equal to infinity, it will be short circuited. Definitely will get some output in terms of Vin. We'll get some output in terms of Vin. Why this negative sign? Because it will be altered. Because you apply the input at inverting terminal. So definitely the filter is HPF. Our answer is HPF. Okay. And the same thing we can check, cross check with the expression of transfer function. Now let's do it for transfer function only, because we have to find out the omega 3 dB there. Okay. Now here it's a 0. So 0 minus V in divide by R plus 1 by SC. No problem. 0 minus V naught divided by R2. Is it okay? So finally you will take this to that side. It will become like this. Okay. So the V naught by V in will be minus R2 SC divided by RSC plus 1. Okay friends, so see, this is the type of HPF filter equation. We have seen, right, the transfer function for the HPF was Ks divided by 1 plus St or tau, like this. So we are getting 0. This is 0 and these are the poles. Okay, so we are getting poles also. Okay, now omega 3 dB there. When we have seen earlier that omega 3 dB, there we have seen this is the tau. The multiplier of S is nothing but the tau. Over here the tau is RC. Tau is RC. So they are asking omega 3 dB. Omega 3 dB. So in this case the omega 3 dB was 1 by tau. So in this case omega 3 dB will be 1 by RC. Is it okay friends? So this is very easy circuit. If they are asking omega 3 dB, we need to calculate the transfer function also. If they are asking simple question, find out the filter, whether it's HPF, LPF or band pass or band reject. So we directly can check it. Okay friends. Now another circuit is given. Minus plus. Taking V naught over here. This is the feedback circuit. In feedback circuit, I have R2 with C2. C2 over here. Now we introduce the capacitor in feedback circuit parallel with feedback resistance. Input we applied over here like this, and the non-inverting terminal is grounded. 0. Which type of filter it is? First identify that. See, at omega equal to 0, let's first omega equal to 0, the C2 will be open. If the C2 will be open, the circuit is simple. We'll get output over here. We'll get some output in the form of input. Definitely we'll get. Now let's take omega infinity. Or omega is infinity. Omega infinity, this will be closed. Once the capacitor is closed, this entire 0 will come to voltage V naught. In this case, we are getting V naught equal to 0. So this is the low pass filter. Definitely the waveform will be, the graph will be like this. Is it okay friends? This is LPF. Now they are asking omega 3 dB. Omega 3 dB. Omega 3 dB is 1 by tau. What is the tau for this circuit? Tau for this circuit is nothing but R2 C2. Okay, this is the tau formula. Tau is nothing but RC or L by R also. Okay friends. So this is the feedback circuit. Let's consider 2 point A, B. Across this point the time constant will be capacitor into resistor. So it will be definitely R2 into C2. Now for omega 3 dB we have to divide it. Is it okay? Now let's see the next circuit. Very interesting. Here it's R1. Inductor also. In the feedback part R in parallel with capacitor C. This is the circuit given. Here output I'm taking. Let's take op-amp over here like this, minus, plus, and this is this. Here it's R1, L1, R2, C2. Over here it's V in. Okay friend, this is the circuit. Now the question is same. Which type of filter it is? Find out the filter. and omega 3 dB. So can we find out the filter? See, at omega equal to 0, we'll check. Omega equal to 0. If omega equal to 0, this will be definitely short circuited. This will be open circuited. Definitely will get output something. Okay. See, at omega equal to 0, the inductor will be short circuited. The capacitor will be open. It means the circuit is complete. Nothing is there. We have to just connect it V in, and the circuit will get output. But if omega equal to infinity, in this case, omega equal to infinity, this will become short circuited, this will become short circuited, this will be 0 over here, and the entire 0 will be there at output also, 0 volt. So omega equal to infinity, we are getting see 0. At omega equal to 0, we are getting kV in. So definitely this is the low pass filter. It's passing only low frequency signals. At the high frequency, it's blocking. So this is LPF. Okay, one part is over. Now they're asking find out the omega 3 dB. So for this circuit, let me calculate. Then I'll show you how to calculate directly. So again, we have to find out the transfer function of this circuit, input-output relation, I mean. Okay. So just convert this circuit into the form of, this will become LS, this will become 1 by C2S, 1 by C2S. This is 0 over here. Now I have to apply node analysis as 8 point A. So it will be 0 minus V in divided by R1 plus L1S. Okay. Plus 0, here it's minus V0. Minus V0 and the parallel combination of R2 and C2S. If you will resolve this, it will become R2 into 1 by C2S divided by R2 plus 1 by C2S. Okay. So resolve it first. So this will become, this is R2 into this is 1 by C2. This is 1 by C2 given only. Okay. So this is R2 C2S. Here it's R2 C2S plus 1 divided by C2S. C2S will cancel out. We'll remain with R2 C2S plus 1. So this is your resistance. So R2 C2S plus 1. Is it okay? Or instead of this, put directly. I think it is complicated. Let me clear what direct mean. I'll show you. See, instead of this parallel combination, we take 1 by 1. So equation will be easy to solve, right? So 0 minus V naught divide by this 1 by C2S, 1 by C2S plus here 0 minus V naught divide by this is R2 equal to 0. Okay. So this is the equation in which V in and V naught is over here. Now let me resolve it now. So if you will resolve this equation, you will get V naught by V in equal to, writing directly, okay, 1 plus R2 CS like this, and we are getting R1 LS also like this. Okay. So to compare with the standard form, I should be 1 plus S tau form. So here I'll take R1 common. If R1 will common, it will become 1 and it will become L by R1. Okay. So this is the transfer function we are getting. And this is the transfer function related to LPF only. This is LPF, no doubt at all. Okay. If instead of R2 it is R2S, then it will be HPF. Now the question is, what is omega 3 dB? Omega 3 dB. Here we are getting two terms. Here this is tau 1 and this is tau 2. So 2 omega 3 dBs are given over here. One is 1 by R2C and second is the opposite of this. It will be R1 by L. So this is second order actually. Second order LPF. second order LPF. Okay, in the second order LPF we are getting 2 omega 3 dB. So which one is lower, which one is higher, I'll show you in one of the examples. Okay, let me take some examples based on this. Let me draw circuit over here. Minus, plus, like this, connected over here. This is R capacitor connected at non-inverting terminal, and to this R I applied V in R. This is grounded, and this is connected over here at the output directly, like this. This is the question given, 1 mark question, gate 1 mark question. Okay, now the question is, the circuit in the given figure is the option A, LPF, option B, HPF, option C, band pass filter, and option D, band reject filter. Okay, so simple question that I'm not asking omega 3 dB, so please do not calculate any transfer function. Directly you can judge. How we'll judge it? Omega equal to 0, let's take first. Omega equal to 0. Omega equal to 0, what will be the state of this? It will be open. So it will be not in the circuit. This one also will not in the circuit. So nothing is there over here. You will get definitely what you will get. You will get something. Means V0 you will get in terms of kV in. Now we'll check at the omega equal to infinity. At omega equal to infinity, now we will check. Okay. At omega equal to infinity, infinity means the capacitors are short circuited. The capacitors are short circuited like this. If this is short circuited, this entire thing is over here. This entire thing is over here. So V0 is 0 definitely. So V0 is 0. So this is clearly shown over here. This is low pass filter. So this one marks in 15 seconds low pass filter. Okay friends. Now let me take another problem. The problem is given 2 marks problem. And the problem circuit is V0, inverting terminal, non-inverting terminal. At inverting, we are connected with 10K, no problem. And wait a minute. And over here you are connected with 10K. This is grounded. Capacitor with capacitor input V in, 1K grounded. Okay, so this is 10K, 2 marks question. The question is, the op-amp circuit shown in the figure is a filter. The type of the filter and its cutoff frequency are, the cutoff frequency they are asking, and filter. Which type of filter it is and cutoff frequency. Omega 3 dB means, okay. Options are given. Option A given, HPF and 10 to the power 3 radian per second. Option B, LPF, and this thing is same. Option C is given HPF with 10 to the power 4 over here, and D option is given LPF with 10 to the power 4 over here. Okay, so first find out filter. It's very easy to find out filter. Let's take omega equal to 0. Omega equal to 0, this will be off. This will be off, means nothing will go at the output because you disconnected input. This is off. Here it's a 0. 0 will go at the output stage. You will get V0 equal to 0 definitely. Why? Because you disconnected input. No source is there in the circuit. The circuit it is dead. So at the output you will get definitely 0. Okay friends. omega equal to infinity now. At omega equal to infinity, it will be sure the circuit is something, and in this circuit definitely you will get output in terms of V in. In terms of V in, you will get the output. So this is HPF. So you are remained with these two options only, whether it's HPF with 10 to the power 3 cutoff frequency or 10 to the power 4 cutoff frequency. Now for the cutoff frequency, we have seen that you can form the transfer function. Once the transfer function will be there with you, you can find out 1 by tau. 1 by tau is nothing but your omega 3 dB. Is it okay? But for this question, don't do like this. Directly see, this is the circuit who is introducing time constant or time delay. Is it okay? Or the frequency component, because capacitor is the frequency dependent component. So across the capacitor, the tau is always RC. If you have R and capacitor, so tau will be, the circuit is disconnected over here because I taken by the op-amp is always 0. So you are having time constant R into C. What is your R? It's 1K. What's your C? The C value is 1 microfarad. So it will be 1 milli. So 1 milli is your time constant. Now your omega 3 dB is 1 by tau. So it will be 10 to the power 3. So for this question, your answer is HPA with cutoff frequency 10 to the power 3 radian second. So friend, this is all about this session. In the next session also, we'll continue this miscellaneous topic. These are very important as per the GATE exam. So I have to finish it. Once I'll finish all miscellaneous topics, I'll come with the 4th unit, oscillation and power amplifier. Okay friends, we'll meet in the next. Till then, take care and bye.